Welcome back to Inside Astronomy. It's nice to be able to film outside now the weather's improved and the rain has gone, which has only just stopped about half an hour ago, but the sun has come out again and well, let's hope it stays nice for the rest of the weekend. Today we're going to be talking about reducers. The reason is pretty simple. There's a lot of, let's say, misinformation online. Some information is I hate to say deliberately misinformed, and some of it is just not well explained. So in this video today I hope to go through reducers, why you'd want to use one with your telescope and what benefits it can bring to you, because they do bring benefits. And I have reducers for 3 of my telescopes, and 2 of them are for a different reason. One that you will probably also have an issue with potentially, especially if you're imaging in a similar condition to me, Northern Europe. So let's go through why you want to use a reducer and how they can help you to improve with your astrophotography. And I was quite surprised when I did some research online, looking online at the different systems diagrams that are available for Takahashi telescopes. I was expecting more information, to be honest with you. My particular telescope, the TOA 130F, is now about, well, getting on for 18 years old. So I have my system chart here. I'll inlay this on the video so that you can see in more detail the chart. But what I found really surprising, and again, this piece of paper, this laminated piece of paper, is also as old as the telescope. But what I found surprising is a piece of information that was missing from the system charts I saw online. And that is here. Again, you'll see it better in the inlaid video. There's a table here that tells you the focal length and the image size that you will get with, it tells you the focal length and the image circle you can expect to get with the different reducer options. And as you can see, and I'll point them out on the inlay as we go along, the reducer itself can be used on its own, or it can be used with rings. It can actually be used with a total of 3 rings to give its maximum reduction in the telescope itself, which would give you an image circle of 40 millimeters. So I use my reducer with 1 ring, and one thing you learn pretty quickly about Takahashi telescopes, well, the reducer itself is expensive, but so are these rings. So basically, this is my reducer. Comes with these nice caps to keep everything clean and tidy. Again, it's an expensive piece of glass to buy for a telescope. But it's a very important piece of glass for a telescope, and we'll discuss why it's an important piece of glass. Now, natively, let me just screw this back on and put it to one side. Now, natively, my telescope, my TOA 130F, is an F7 telescope, which is pretty good for that type of telescope, and considering the telescope is getting on now for 18 years old, that was pretty fast at the time. Most telescopes were in F9, F8 at that time. Now, using the reducer, I can actually bring the telescope speed down to 5.8 and about exactly 750 millimeters focal length. And that, if I refer back to my chart, and again I'll put the inlay up for yourselves, gives me a 50 millimeter image circle. You can see that the telescope was originally designed to fully illuminate a medium format camera. Not many telescopes are built like that today, but the Takahashi TOA was built like that, and the original image circle of the telescope was 96 millimeters. That's huge, especially by modern telescope standards. The more realistic 50 millimeter is still a large image circle for that telescope, but you can see it's not much of a sacrifice to use the reducer to get that extra speed and benefit from shorter imaging times. In fact, with an APS-C size sensor, I'm still fully illuminated, so literally no sacrifice at all. Even with a full frame sensor, a 36 by 24 millimeter sensor, there's no sacrifice because the sensor will still be fully illuminated even with that reducer in place. Now, I have made 3 slides to help us to go through how a reducer works and what benefits it can bring for you in your astrophotography journey. So let's go through them now. I'll inlay them in the video for you so you can better see them as I talk through them. The first slide tells us what a reducer is essentially doing. Now, essentially when you put a reducer into your telescope, you are making the light rays converge faster, so they're appearing to converge from a shorter focal length telescope. Now that is effectively reducing your image circle. Now if you have a telescope with a very big image circle to begin with, that's not much of a sacrifice, of course depending on what sensor you're using to make your images. Now my telescope here that I've made the slide on is the TOA 130F. It starts with an original image circle of 96 millimeters, a huge image circle by any standards. The telescope was designed to fully illuminate medium format cameras. Probably many of you out there don't know what the hell I'm talking about when I mention medium format cameras. Essentially it's 3.5 times bigger than a full frame sensor, 36 by 26, because the size is 6 by 6 for medium format. That's 6 centimeters by 6 centimeters. Now what placing a reducer into my telescope does, it will essentially reduce the image circle down to 50 millimeters. So by doing that, it's shortening the focal length, or shortening the apparent focal length of the telescope to 750 millimeters instead of the 1000 millimeters at f7. And it's concentrating the light that would have been spread over a circle of 96 millimeters in diameter into a circle now of only 50 millimeters in diameter. Now of course for me 50 millimeters is still very good. It fully illuminates all my astro gear that I have here. In fact the biggest sensor I do have is full frame, 36 by 24. But by concentrating the light down into that smaller image circle, we benefit from the telescope going from f7 to 5.8. And here, if you follow along with the calculation I've made, and I've given you the formulas because I don't want to hide anything here. Again, one of the missions here is to put the science back into astronomy and to give you all the information you need to verify what it is I'm saying, rather than just being based upon, opinion. Because let's face it, qualitative data or true empirical data is far better than anyone's opinion. So even mine, I might add. Quantitative data that you can repeat the measurement for yourself, and you can do this for yourselves with these formulas, then you can confirm that what you should be seeing is actually what you're getting. So the light intensity is inversely proportional to the square of the focal ratios. Therefore, the change in intensity is equal to the square of those focal ratios. So now we take f7 minus f5.8, square that, what do we find? What we find is we're getting 1.46 times more light in the image circle that's only 50 millimeters in diameter, rather than the original image circle that was 96 millimeters in diameter. So that's how a reducer speeds up your telescope. It's not magic, and there is a compromise here to be made. However, I think it's a compromise that many of you can easily make, especially if you're working with a micro four thirds size sensor or an APS-C size sensor, and even a full frame 36 by 24 millimeter sensor in this telescope would still be fully illuminated. However, let's be honest, that's not the reason I put a reducer into my telescope, at least not the main reason. It's not the first thing I think of when I want to use a reducer. What I actually think of is the object I'm trying to image. Will it fit onto my CCD sensor or my CMOS sensor, and how does it fit? Does it fit nicely, or is it squashed in there? How compact is it? And that brings us on to the next slide. So this is the primary reason why you want to have a reducer with your telescope. And I would honestly say today, unless you're buying an astrograph type telescope, which is already fast enough and giving you that fully illuminated flat field, you need to be buying into a telescope system with a dedicated reducer. Why would I say that? Because if you have a dedicated reducer for the telescope, that reducer is probably also taking care of some of the optical aberrations at the same time. So a reducer stroke corrector, so to speak. And I think that is certainly true for some of the William Optics type telescopes with short focal lengths, things like the Red Cat. I think field curvature is probably better controlled with the reducer in place. But anyway, other people need to confirm that, because that's not a telescope that I own. But you do get reducers that also correct optical aberrations in the same telescope system, because it's a known platform. It's a known system to that manufacturer, so why wouldn't you do it? So what you can see here now is using Telescopus, I've set up the images on Andromeda, and you can see that with Andromeda set up at 1000mm and f7, it barely fits into a full frame sensor. It's just about squeezing in there if I rotate it, put it on the diagonal across the image. However, if I put the reducer into the telescope, an image at 750mm, which gives me the benefit of that additional speed at 5.8, Andromeda easily fits inside the framing, and in fact I could even change the framing a little bit. It's not longer necessary to have it completely on the diagonal, and I've got more options here available to me to set up the framing of this DSO. So the main takeaway for you as an astrophotographer is that a reducer gives you more options with framing DSOs and allows you to get your image scale correct for your target. That is and should be the primary reason that you want to use a reducer in your system. Okay, so let's go to the last slide. I promise you this is the last one, and this is why I use the reducer on my other two telescopes, as you'll learn now. The other important point when putting a reducer into the system is that it changes the pixel size. Each pixel on your sensor sees a certain amount of sky, and as you've already just learnt now, by putting a reducer in, a pixel will see more sky with the reducer and will therefore be brighter. And I've explained why that happens by placing a reducer in your image system. The reason that I use the other two reducers is because my imaging systems that is directly behind me, and it's a RC, it's a 14-inch RC, but that RC has a focal ratio or focal length of nearly 3 meters, 2,800 and something f8. Now there's no way I can take advantage of that here under Dutch skies, absolutely not. And the same goes for the Mulan, which is a smaller telescope, 10-inch, but still 250mm focal length. There's absolutely no way I should be using those telescopes at their full focal length here in the Netherlands. So let's take the most common pixel size that on the modern cameras, modern CMOS cameras that you can buy today, and let's do some calculations to see what my image resolution would be using that pixel. So I believe that to be 3.8 microns. It's certainly true for all the TubeTech ZWO cameras. It seems to be the most common, and certainly if you're within, you know, a few percent, 20% of this size of pixel, these calculations will work easily for you as well. Certainly rule of thumb, as we say. So what I've done in this slide, I've calculated the constant for you to convert from radians to arc seconds. If you want to know how to do that, it's very easy. It's just a little bit of mathematics, high school mathematics, nothing more than that. Radians are basically, if you remember from high school, 57.29 degrees is 1 radian. It's not precise, but it's good enough for most applications. If you want to calculate it precisely, then you just have to take 360 degrees, the full circle, divide that by 2 pi. Because pi only gets you to 180 degrees, so 2 pi brings you to 360. So 360 degrees divided by 2 times pi will give you the precise will give you precisely what 1 radian equals. Now, if you times that by 60 and again by 60, you get the constant that you need to get to arc seconds, and that is 206,264.8. Now, what you can do here is take your 3.8 micron pixel and make that calculation. Now, I've done it for you in the slide, but now you know how to do it for yourself, for your own telescope, for your own system setup. And I find that even with a telescope that's only 1000mm in focal length maximum, at f7, I'm getting a resolution of that pixel to be 0.783 arc seconds. I mean, come on, that's impossible. I'm never going to see that kind of sky condition here in the Netherlands. I mean, forget it. Now, 750mm at f5.8 gets me to 1.04 arc seconds. Again, I'm not going to see that. My average seeing here in the Netherlands, I would estimate to be anywhere between 2 to 3 arc seconds on a good day, and anywhere between probably 3 to 4, maybe a little bit higher than 4 on your on your average day here in the Netherlands. So, you know, I'm not up a mountain. Most of the Netherlands here is 3 meters under sea level. I can actually at least brag that I'm probably 3 to 5 meters above sea level, but it's not much. So I'm not going to get to those kind of resolutions. So now imagine you've got a telescope like the Milan that can work at 2.5 meters, and you have the telescope behind me, the RC, that can work at nearly 3 meters focal length. There's absolutely no point in doing that, and I don't. That's why both those telescopes also have reducers. So I can benefit from the additional speed, and I can bring the focal lengths down to something that's at least a little bit more manageable for the sky conditions here in the Netherlands. The only exception to this, of course, would be if you're doing planetary imaging, and there you would use a Barlow to extend or increase the focal length because the planets are bright. But that's a different kettle of fish and not something we're talking about today. So with the reducer in the Milan, it brings that telescope down to around about 1800 millimeters, and I know because I'm imaging currently the Ring Nebula with my RC that the astrophysics reducer, and I'll put the inlay of the astrophysics reducer there, I'm at about 58 millimeters, so I know that I'm around about f6, just under 5.8. The reason why I'm not very precise on this is because to confirm that measurement, all I do is a blind plate solve, and of course that then confirms the telescope focal length. I know I'm around 2 meters, or if a little bit under 2 meters. But that gives me a fantastic telescope operating at f6 for imaging galaxies, which you know is my favorite subject, and of course the project that I'm on at this moment in time, the Ring Nebula. So there's another reason why you would want to use a reducer, to make the telescope more versatile, more useful to you. In fact, you could almost say, depending on the reducer that's offered with your telescope, it gives you almost 2 or 3 telescopes in one purchase. And that's why it's my strong recommendation that when you look to buy a telescope today, I would only look to buy one with a dedicated reducer system for that particular telescope series, because I think then you will get the maximum benefit from ownership of that telescope, working on various objects of various sizes in the night sky. Because let's face it, that's the other issue you have, what you first realize when you get into astrophotography. The nebulas, the different types of nebulas, for example, Cygnus is high at this moment in time, and you've got the North American and Pelican Nebula. It's a huge complex, an absolutely massive complex that you would struggle probably to put on a medium-sized refractor with a full-frame sensor. Being able to move your telescope up and down its focal length is a huge benefit in your ability to frame these objects up and make the images that you want to make in this astrophotography journey. Now, I hope that's demystified what reducers can do for you, how they work, why they brighten up the image circle of your telescope and make your telescope appear to be faster. And I wish you the best of luck in this, right now a very changeable season. Let's hope we have some clear skies soon, and with that I'll say goodbye for now.